Okay. Thank you to be here for the lecture of today. Last time we started reconsidering the system of two states, current and velocity. Any system of consisting of two states can be more or less represented, at least roughly speaking, in this form here. And what we have seen last time is what we started, that assuming that our necessity is to estimate not only the two state variables, in this case, current and velocity could be liability and asset, could be any kind of state, but also any parameter of the system. For the engineer, it's quite clear. For instance, I can consider to estimate the resistance. I can consider to estimate the inductance. I can consider to estimate parameter, which you can find here, J, Kf, Km. How many parameters can I estimate? We will answer in January when we will consider the observability concept inside the nonlinear system. Why that? Because we will see if the representation is this one, which we considered here, we are considering the parameter R as an augmented state. You remember, I told you many times about this augmented state. The first time when during the estimation of the unique variable which we have. Do you remember? Again, the name was R, the variable. In this case, R make more sense because we are considering a resistance. But do you remember the first example, the first application in the context of Kalman filter, which is in this lecture, was using R, the variable R, which was in a Gaussian variable. Gaussian means I don't have a model. We have just its Gaussian structure characterized by variance of R. Here, nevertheless, is variance, covariance, because it's inside the system. R appears here, but appears also in let me say, row, column of the states, and this row of all zero is exactly what we have seen when we have just one variable. Do you remember? The R with respect to the t, the derivative of R with respect to the t equals 0. Here, of course, is a little bit more complicated because R interacts with the rest of the model. Why is this nonlinear system? Even though it's an artificial nonlinear system, but in the sense that we represent as a nonlinear system. Because we want to estimate. If we want to estimate, in this sense, we need, in accordance with the structure of the Kalman filter, to include this variable inside the state variable. Yeah. Therefore, appears as an state. But as an state, we multiply two states, R and I. This means we have, or that we are in the present, in its representation of a nonlinear system. In this sense, the representation is nonlinear because of the augmentation which we generate an extended Kalman filter. About the extended, I told you a lot. This means this is the output matrix. We have just to add the state R. Once I realize the discretization, I can realize the discretization in this form here, or I can realize the discretization let me say manually, but in any case, we obtained this field in both cases. I can use this method here. I can apply directly the forward Euler here is I didn't write, but this is the forward Euler because it's written here if you want. Even though formally is not totally correct, but it's not wrong to write everything in form of matrices, but can be done. We can obtain nevertheless this structure here directly. I don't know if I have here. No, I don't have. Applying the definition of forward Euler, which I told you 2 or 3 weeks ago. Anyway, this is the model. Better to say the discrete form of the model, which in the context of a Kalman filter, the forward Euler structure appears in this form. Last time I told you. This means this is let me say, see if I have is basically the equation A, which is not too different with respect to the linear case. Of course, we don't have the matrix A and B. We have the model in nonlinear form. But formally, is F. Why F? Because we don't know which kind of relationship we have between X states at the correct state, a previous step, and the input U K-1 because of forward. But basically, it's the a priori estimation using the model. Everything which I know from the system. In fact, we don't have here any stochastic element. This is concretely this. We can see in particular that's RK from the last line equal RK minus 1. We can see here RK minus 1, which multiply the current, which realizes the nonlinearity. And then if you think about the approximation of Taylor of the, let me say, second equation B, basically the approximation of the dynamics of the a priori estimation error. Here's the definition of the Jacobian. The Jacobian is the matrix of the partial derivative. Do you remember last time I told you that is basically in a Taylor approximation because we are using the partial derivative matrix, the Jacobian. Of course, in gymnasium, in high school, we have seen in just one dimension. Here, of course, if we have more than one dimension, we have to consider the connections in between. But this element here is the derivative, if you look at the definition of ik with respect to k minus 1, if you look at this expression here, it's easy to see that we have just this element here. Of course, it's in a formal derivative. It's the derivative of ik, which is this expression here, with respect to ik minus 1. I can consider also the derivative of ik with respect to omega of k minus 1, which is minus this element here. You can find here. You can check alone the correctness of this J, which basically replaced, I don't know if you remember, our A matrix in the equation B. Equation C and D, A does not change in this case because we don't have nonlinearity in H. I don't know if you remember. If you don't remember, I can come back on the lecture of last time. But basically, the difference is, yes, I can show you here probably. The difference is just here, in which we have, you can see a JA and JA transposed instead of A and A transposed, because we have, what is the idea of Kalman? Is the approximation of the a priori error covariance. Let me see if I forgot to say something. The rest, we have seen now many times this Kalman filter structure. In this case, does not change because H not capitalized equals H capitalized. Do you remember the idea? If we will see together, if the nonlinearity is in the output, this means we have to be a little bit careful. We have to be a little bit careful for the rest of the Kalman filter because in the rest of the expression we have this Jacobian of H. I don't want now to insist on this. We come back on this topic here. At this moment, H is our 100 everywhere. Let me say not capitalized equals capitalized because we don't have nonlinearity in the output. I will come back on the nonlinearity in the output in the next lectures. Yeah, I think we can try to to run the simulation in order to do some exercise, and then I will propose another exercise on this topic here. Let me see if I forgot to say something. Last time I told you about a little bit more about the Taylor approximation. I think it was the last part of the presentation. I don't want to insist on this. It could be that I can come back. Let me discuss again everything using the simulation, because as I told you, in particular on Bachelor, we are more oriented in applications. But anyway, H not capitalized equal H capitalized because the nonlinearity is not in the output. No? You can see the output is characterized by a linear output. This means forget at this moment this Jacobian of H, not capitalized, which became or becomes H capitalized. At this moment, we concentrate on J, because of course the nonlinearity or the nonlinearities must be linearized in accordance with this concept of the linearization. Extended Kalman filter, this means that we linearize the nonlinearity which we have in terms of a priori estimation error, equation B, and a posteriori estimation error. This means, if you want, let me nevertheless repeat a little bit. It's not so bad to repeat this concept. Yeah, of course, any question are possible.
Because I have MATLAB downloaded and now I click on Simulink, or does it need to be something else from here? Or just these two?
At this moment, this is enough, I think, Simulink, because if you download all the rest is also possible, but it could be that takes a lot of time. And then if we realize in our application that we need more toolbox, you can at any time to download. In my opinion, the system should recognize automatically. You don't need to do any further action. I'm not sure, but it should work. It's really clever. Again, on this, let me show you what I intend to repeat now. Yeah, as I told you, here the equation B, instead of A, we have J. J here is formally represented here. And we can see that in C, nevertheless, we maintain the nonlinear, let me say, expression, nonlinear expression, but of course, without the everything which I know, basically, without the stochastic elements. And in equation D and E, basically in the results, we have this H capitalized, which is the Jacobian of H, not capitalized, calculated at the actual predicted state, which is the information which I have at disposition. At this moment, as I told you, we don't have difference with H capitalized and H not capitalized, because in our expression, in our example, is the system linear in the output. Let me now try to show you the simulation, which Senna, you can use also in your thesis. I am trying to estimate the variable R, the resistance, inside the motor. We have seen last time the motor linear case. Now we have a nonlinear representation, a little bit artificial, because we included an augmented R Gaussian, which multiply the current again for Senna, which is exactly also your case. Let me coming back on the lecture. Let me share this if I'm able to do. Yeah. This R of K after the digitalization, R of K or R of K minus 1 in this particular form, multiply I is our nonlinearity, which came from the representation in continuous form, which we considered R as an augmented variable to be estimated. Is our lambda. Is our lambda. We will see. Do you have time later? A little bit? Yeah. Because we want, in this case, also monitor, estimate R, which helps, nevertheless, to estimate the current and omega, because the current at omega depends, the current developed depends on R. R change is not constant. This means it makes sense to give up to the linearity, because we can consider R of t as a function of t. This means we have an linear time variant system, but in this case, we have to know how R of t changes to preserve the linearity. But this sometimes is not so easy to have, because R of t change, okay, R of t, it could be that we can have also a good model. But in any case, now we will check what happens if R of t is not known, and we assume to be a Gaussian variable. As in the first example. You remember, R was, the name was R, but in a variable, in a Gaussian variable, without model. Also here, I don't have knowledge about RT. I assume, this is a little bit, of course, the restriction, because the assumption is that R of t is a Gaussian variable. Is the Gaussian variable, is not the Gaussian variable? Of course, the assumption is not exactly, does not reflect the reality. But nevertheless, we will see that the result will be not totally far away, because if you think about that, R of t could change with the fluctuation of temperature. I mean, the Gaussian distribution is not always, I mean, guaranteed is not yet assumption, is an idealization. But you know that the Gaussian distribution is often considered a natural distribution. Normal, we say distribution. Why normal? It's not always the distribution which reflected the whole phenomena in the physics. But if you think many phenomena in nature reflect this Gaussian distribution, therefore normal distribution. Okay, let me open MATLAB. I uploaded already the file in my study. Let me look here. You can see, I don't know if I share. Let me see if I share. Probably I didn't share now. In my study, you can find these three files. Look. You can see there are more than 3 files, but basically we have the data file, the motor, which you already know. Then we have the main file in Simulink. In order to answer your question, if you build the main file in Simulink, typically it's easier. Now, for the project which we have together, I don't remember because it's in the project which we closed 2 years ago, something like that. It could be easier in paid. We have to look together. But it's not bad if you learn also Simulink. Believe me, Simulink MATLAB. It's not bad because you enlarge your knowledge and you can write also in your CV that you work with Simulink MATLAB. This is in technical field probably is not your task, but why not? MATLAB Simulink is very often, yeah, Sena, required in your company. They work with MATLAB Simulink, right? This means it's not bad if you learn also MATLAB Simulink, not only R, not only. I think it's appreciated, no? Sena, you realize that in technical field, if you know also, no? This means we will see together. No? But here is I have to do MATLAB Simulink. I told you why. Because for different reasons. First of all lectures are organized in MATLAB Simulink. I can a little bit also Python. But if I have to rewrite everything in Python, we cannot do all the lectures, believe me, because so many information in the lecture, no, is clear. And then we have here the licenses with the, let me say, agreement that I have to hold the lecture in MATLAB Simulink. Otherwise, we cannot justify so many money for the licenses. Okay, let me open the. This file is known. Is exactly what I already told you. Here we have something which is not exactly correct. Please keep in mind, this is not forward Euler. This is the exact discretization, which I don't have time. I don't to clarify what is. It's not the form of discretization. We came directly from MATLAB. It's a little bit advanced. If you don't like, you can copy the forward Euler. We can copy the forward Euler. In some cases, how's in this case here, if the model is relatively easy, let me say, we don't have many differences in between. But using this C to the M without any options, the name is exact discretization, which is not exactly forward. I don't have time to tell you what is, but you can use nevertheless. If you don't like, you can. Last time I told you that this. I can do that later if you want. I can write for you. I mean, what is the forward? The forward is I think here. Let me see. Yeah, and system 2 times 2. TS, I think, is the simple time. Let me see. Yeah. We multiply AR. At this moment, let me comment. No? In order to repeat a little bit for you what we did until now. BD1 is equal TS, which multiply BR. And I don't know if you remember, CD1 is equal CR. And D1 is equal DR. Let me comment also this too. Later, if you want, or at home, you can redo that to look at the differences. Let me run the data. Now, running the data, you can see here on the right part, in the workspace, that the data is there. This means we are ready to start the simulation. Let me open the main file, which is realized in Simulink. Of course, you can realize everything in MATLAB, but in my opinion, it's more difficult because Simulink offers integral, after products, realize in extremely intuitive form this feedback. Everything must be built in MATLAB. I can do that because when I started with one of the first version of MATLAB, we didn't have Simulink. I'm still able to do, but sometimes we need to do. But in order to speed up the lecture, in order to, I would like to say, understand sometimes better the dynamic of the system. I don't want to renounce to use Simulink. In the company, Simulink is used. Yeah, it's used because you save a lot of time. It's intuitive, graphically intuitively, or more intuitively to proceed. You can proceed more intuitively, excuse me. Okay, 1 second. Look, let me share. Yeah. Let me share Simulink. I don't know what you see. Probably not Simulink yet. Let me see now. I think you can see Simulink. Yeah, excuse me. This scheme is quite similar as before. We have the motor here. Look, I put also a controller. Then I put also a controller here. Is necessary? No, it's not necessary. I don't know why it's there. It could be that the system doesn't work. I found that the first file which I found is not necessary because now we are not analyze the controller. It doesn't matter which kind of signal we have here. It doesn't matter. It's not exactly correct because the system is nonlinear. We will see when in January I will tell you about the observability, that the observability could depend of the input in nonlinear cases. We have seen at the beginning of the semester that the observability in linear cases does not depend of the input. In nonlinear case, I flesh out just the test on it without telling you many things about that. Depends of all the input. This means when I say it does not matter, it's not so correct. Everything is, as I told you last time. What is the differences? The difference is I measure here the current. Oh, no, here I'm measuring the velocity, it seems. Yeah. to change, I think, to change, because in the M file, I have 1 0, right? Let me see. 1 0, right? The M file. Here, if some students ask me about, of course, change the tuning. Change the tuning because I'm considering now as measurements something which belong, something which is characterized by the dynamic which is in the second equation. This means, of course, it could be that I need to tune in a different form. I don't remember why it is so. I hope that it works. We will change later. The important difference we can realize also from this overview that you can see that we try to estimate the R, not only current at omega, but also R. And as I told you, the estimation of R, which change now over time, I show you now, influences also the estimation of current at omega, current and velocity. Here it seems to be that the real value of R is 12. But Kalman does not know exactly this. I told you why. Calmness is here inside. Now we can see 3 states instead of 2. In the example before, we had to now just x1 and x2, current and velocity. We have x3, which is R, our augmented state, our lambda set. If I go here inside, here K is here. I don't have time here in this codes to it's not needed for the next step. But sometimes it's used to tuning or to the bag, to tuning also. But in this course, it's too complicated. But anyway, to monitor what happens in the Kalman filter. Because you remember, K very small means to trust the system or the model of the system. K very large means to trust the measurements. This means K is important to understand what Kalman filter is doing. But it's too complicated in its course. It's used also for tuning Q and R, but in general, it's useful to monitor what Kalman filter does. K, do you remember? K very large means, remember, the correction is a priori knowledge plus K, which multiply the innovation, what came from the measurement. If K is very large, I emphasize what came from the measurement. This means K is important to analyze in order to look, to monitor the behavior of the Kalman filter, what Kalman filter does. But at this moment, it's too complicated. We can consider eventually together in the project or in the future. At this moment,
Sorry,
yeah.
I have one question. So I understand it with K, but can you explain it with T? I didn't quite understand. If T is smaller, then we trust the model more, right?
T,
Other way around.
what do you intend with T?
I thought you said it about, like, you explained T and K, where like if we put the values, if the value is high or low, or if we put more emphasis on one value, then we trust the model more or less. So, or we trust now you explained that we trust the measurements more, but didn't you say something with T, or did I just mishear that?
About the trusting concept is basically just 3 things are relevant. Q, R, and P0, the starting point of the a posteriori, let me say, error. T, we don't have T, we have a TS sample time, but this is not connected with the trusting. Probably my pronunciation was not clear.
Okay, sorry, then okay,
In
because
K,
I was wondering.
no problem. Ask everything. K depends on all 3 things. I show you why. We have seen also, I can show you also here. Let me go ahead and then I will change value of Q, K, and P0 in order to show you how K depends of this. Of course, if I change TS sample time, everything change, but change Q, I have to change Q, R, and P0 because TS is the sample time, TS, sample time, which characterize the discretization. We characterize the discrete dynamics. This means T, of course, is something which change the results because change basically the model. I don't know if this probably, I tried to explain this or last time, I don't remember. I showed you this probably. If you intend, thank you for the question. TSTS, here, look. T is the time in continuous. This is a physical variable. The time runs, we say also in our life. Here we have the TS, which characterize the discretization of the T not capitalized, which is our running variable, independent variable. Everything is defined over time. Our life is defined over time, T small, T small. Now, if I observe my life in the context of TS sample time, fixed time, this means I look today, I look tomorrow, I look after tomorrow, but not every microseconds. This means today is the information which I have in the morning. Tomorrow I have the information which I have in tomorrow in the morning. Anyway, we have a representation which depends of TS. This representation, of course, characterizes, you can see from here, the a priori knowledge, fix the a priori knowledge. And this, of course, if I change TS, I have to change also Q, R, and P0. Probably last time I told you something like that. If TS is very large, of course, we have an error in the representation of the model. We have an error in my a priori knowledge. Example, thank you for this question, really. Thank you for this question. I mean, if I sample my life each hour, and I write what I'm doing each hour, it's different if I write what I do just in the morning. And I consider valid for the rest of the day what I did in the morning. This is a little bit the concept. Of course, if TS is very large, I have a big error, or a larger error, in the representation of my life. This means I have to consider an Q, something which represents the uncertainties of the model of my life, larger than if TS is very small. It's basically this problem here. In this sense, you're right if you intend the TS as a possible parameter. Of course, the choice of TS influences also the choice of Q directly. The choice of Q directly. I show you what I intend practically. 1 second, it takes something to write. Let me switch on the lateral camera. Remember this. T continues. Assuming that this profile is the profile of my feeling. It's not far away what I am saying. Feeling during the day, starting from 0, which is 0 when I wake up. It's exactly what we did with Osman. Is the master student which realized, is finishing now the thesis, the master thesis in this bipolar disturbance. I will invite you in January when he will present this work. It's extremely interesting. It's something which we found in the in a Finland, in a literature in Finland in cooperation with America. Kalman filter for estimated of the feeling applied to this disease. Disease, I don't know, is a disease and disturbance. Bipolar is a disturbance. I don't know if you know. High, down, high, down. Anyway, as I told you, it depends also from the frequencies, depends also of the peak to peak. I mean, in the morning, basically, I'm not so happy because I don't have energy to start. And then we can understand after breakfast, there's a little bit better. This is normal. What is not normal, if this peak to peak, this peak here, this high and down, is too far away, too high, euphoric, too low, depressive, and the frequency is very high. I change my feeling every hour. Of course, it's a little bit not easy to live with this feeling. And then we have a controller. The Kalman filter realize when this happens, and then the controller try to care this. To stabilize, I don't know, high, or to stabilize low, or to stabilize in the middle. It's interesting because some drugs stabilize high, some drugs stabilize down. But anyway, we didn't test with the drug. No, don't tell us. But in the paper, in this medical paper, they did some interesting consideration. Now, again, of course, this representation and so on, in which instead of this continuous function, I will consider this stepwise function, in which in the morning I will consider for the first hour just the feeling which I had at the beginning is not so precise if I consider an half hour. Because you can see that continuously I'm improving. I'm feeling, let me say, a little bit better. No? Better, I don't know. No? But anyway, the feeling is a little bit higher. No? Of course, the representation, in the red representation, half hour representation, just to understand, half hour just, I don't know, could be also 1 minute, half minute representation if the blue TS is the minutes representation. We have a better, precise representation. This means Q should be smaller for the red instead of the blue. But once this is fixed, K depends of Q, R, not R, the variable R, but the Gaussian variable R. I called here W, I don't remember what. And P0. Let me simulate and let me repeat this extremely important concept about Q, R, W. This means this stochastic value. We have the mismatch in the variable. We have R variable resistance, and I don't remember how I called. Let me show you. Let me open the Kalman filter here inside. Did it open? Okay. Yeah, RW. This is the variance of the measurements. In this case, I am measuring omega. What is this file here? This file here is the file which is, let me share. Here inside as an embedded, as an interpreted file. Now, today we will see a case with an embedded file, so we learn both. But in this case, it's also again interesting to look didactically at this feedback and so on. Here inside, let me share. In this structure here, we have this interpreted file with the name which I told you, no? With the MSNM file. Now, let me show you what we have. It is working. And then we will try to play with QRW, excuse me, QRW and P0. At this moment, look at P0 because K depends basically on these three parameters. Once TS is fixed, again, TS very large implies Q larger, or the very large if you want, because Q represents the variance of our representation of the reality. If TS simple time is larger, of course, we don't have a good representation. The example of the life is a good example. If I represent my feeling for 1 day, I lose this variation in 1 day because I approximate the feeling just in the morning, each day. If I want to represent this this disease, this disturbance, let me say, this bipolar disturbance, TS, should not be 1 day, because this disturbance is characterized per hour, in accordance with what we learned from the medical literature. It makes sense. No? Just considering that in the morning, also normal people, normal in the Gaussian, more or less we are more depressive than, I don't know, after lunch. I don't know, I am speaking for me, no? But it makes sense. To start in a process is always not so easy, because we have to overcome an inertia. No? We have a state, we are sleeping, we have a wake up, insulin, everything which is involved in this. Why I speaking about insulin? Because even a project in Kalman filter, I would like to applaud this project in my study with insulin. Insulin, I mean, diabetic control using injection of insulin. It's clear that in the morning to wake up, we have to really have an impulse in insulin. This is not so easy for everybody. In general, it's not easy. Because we have to change from a steady state situation. I don't know if you understand the steady state situation, when we are without change, not a steady state, and then we have to change. That is, roughly speaking, each change is not so easy. In particular, if the change is not positive, and if we're waiting for a day really strange, we don't want to wake up. But anyway, this is more complex. Look at this. What I am saying here, for instance, that we are really far away from the real value of omega. This means the Kalman filter estimating omega, we will get an impulse very strong, because it seems to be, or at least Kalman filter interpret that we are far away from the goal. In fact, look, let me go out from this. Oh, why that? If you look what I wrote here, oh, very interesting, 200, and I don't know what is the real velocity, I will tell you, but I would like to show you that here I put, no, excuse me, 1000 is related to R, excuse me. This big value is related to R. It's not omega. I mixed with example last time. It's better if I repeat, excuse me again, because I had in mind the exercise of last time. Why I put here this big value, and here we have a very small value, because probably TS is very small. This means the dynamics are represented very well. And this for this value here. Moreover, probably the initial value of the current here, and the initial value, moreover, the initial current of the omega is not totally far away. Very interesting in this parameter here. But anyway, it seems to be very small, this. But I would like to discuss this. Why I put this? Because probably I put the value of R totally far away to check, totally far away from the reality. In fact, let me show you. Let me discuss the third element now. Let me share this. In fact, look. Here, we have a not realistic value. It is impossible to have a negative resistance. Engineers understand very well. This means I have to inform the Kalman filter, please pay attention. Go far away from this initial condition as soon as possible. Because if you remember, the EKF extended Kalman filter does not guarantee the stability. It could happen that I will not converge at all. Here we have a 10 and 200. In accordance with what I wrote in P0, it seems to be, again, P0 is just related to the initial error. I told you about the discretization. Excuse me, I make again a little bit confusion. It's just related to the initial error. This means the initial error of the current and the initial error of omega should not be so strong. But in R, is extremely strong, the error, very large, let me say large, because it's negative. R cannot be negative. Just with an example, doesn't make sense to write minus 100. I put just to show you that the Kalman field is so clever that understand that should far away from this critical situation, not physical situation. Now, excuse me again, P0 is just characterized by the initial error if I know information. Now, it seems to be that we are relatively close to the goal. It could be not valid, this assumption. This means it could be that Kalman field needs time to go far away from the condition of initial condition from current and velocity. Let me show you. Yeah, I know that is not so easy to follow this, but if you do at home some exercise alone, just to move initial value, to play with the Q and R, it's not so difficult to understand. It's easier than to explain. Let me show you in real case. What is our real case? Now we know the real case. In practical application, we don't know the real case. No, God knows. But now we know the real case because we put here inside. Yeah. Oh. Nevertheless, what we wrote in the Kalman filter does not reflect the reality, because here we have to, in the P0, we have to write the variance of the error. Basically, we are saying that we are very close to the error. Let me say roughly, we can also calculate, but it's not valid. One is 10 instead of 0. The real value is 0, and we say that is 10. And the other is 100, the true, and we say that is 200 with extremely high precision, because the value was extremely small. This means I am waiting for very small, very slow approximation of the current first variable, very, very slow, let me say, slow approximation of the velocity. Of course, this could influence, nevertheless, the approximation of R, even though R, I say, please go ahead, go far away from this. Let me show you what happens, because everything is connected. Theoretically, I have to be consequence, but of course, no, God knows this. But assuming that this is the knowledge which we have, wrong knowledge in terms of current and velocity, wrong knowledge in terms of first and second variable. Let me nevertheless look at comment what I see in the simulation. Here inside, I don't comment now because it's exactly as I commented last time. But of course, we have 3 variables instead of 2 variables. We have a current, omega, and R. If you want, I can show you a little bit. And then we have also in a covariance matrix, which is 3 times 3, because we have 3 errors, not 2 errors as last time. If you want just shortly, but let me simulate and then I show you. Otherwise, it's too boring, this. Okay, let me see directly what happens in R, assuming that is working, because I am working with really stupid conditions, because cannot be negative. I forgot to define something, or the probably is too stupid, the condition. Let me see. It could be. Let me write in a reasonable value of R. It could be this was the case which we didn't work, and I am not surprised. Let me go here inside, and let me write 0 instead of minus 100, because doesn't make sense, man. It could be this the problem. It could be that the student asked me, now it's more feasible, but the real value is 12. in the data we have 12. Let me see if this is the problem. It could be this. Let me see if this is the problem now. No, again, the error. Let me see which kind of error we have. Well, now we have to find. Let me reduce a little bit this value here, because this is really. I reduce this this value, which could represent could be close to the resolution of the machines. Let me see now. No, again, the error. It could be that's in the problem of the tuning. Let me consider measuring. Okay, let me see. Probably the error is that I didn't change the. No, here is correct. Yeah, okay. It could be, that's of course, this value was just to test. I don't know what they are really strange value. Let me see if this is the problem. Sometimes a student ask me something. Let me start with some more reasonable values. Seems to be not correct. Let me change the measurements. Could be this the problem, that this was tested for measuring. We can see the current. If I measure the current, I have to change also the M file. Let me go inside. If I measure the current, I have to put here 100. We have 3 elements here inside because we have also R, no, as a state. I will analyze later if I am able to have a working files. Let me see. It seems to be working. It could be that, as I told you, if I change the measurement, I have to retune. It could be this was the problem. Let me see R. Let me share. I don't know if I shared. Yeah, this is R. We can see that at the beginning, nevertheless, we have a relative prompt reaction. But of course, this uncertainty in the beginning is due to the mismatch in the P0. With the reality. Of course, this cannot be known, but it seems to be that after 1 second, we can see here, R is estimated very well. Try to do at home to change this R. For instance, we have seen this together, no? Within sinus function, do you remember? Assuming that change over time with the temperature is in a sinus function. It could be that if you have a high temperature, increasing the R. If you are low temperature, decreases the R, the resistance. You will realize that the Kalman filter nevertheless estimates this. Let me see current and omega. I don't know why it didn't work in omega. It could be, again, if now I'm measuring the current, if I measure omega, I have to retune, should work, because the system should work. As an EKF, I cannot guarantee it. But if we are close to the goal, it could be that we are too far away from the goal. You remember the idea I showed you again, what happens in nonlinear case. Let me see the velocity. You can see that the velocity is a little bit lazy, or the Kalman filter is lazy to estimate the velocity, because you remember we put a value very small in P0. Saying to Kalman filter place, pay attention, you can sleep because we are close to the velocity. You remember this? I told you. We can see that with respect to R, we have 2 seconds, no more or less. Twice the time I need it. It is impossible to calculate how much time, because we are in a linear case. Look at the current. I don't have the current here, the comparison. Here, no, I have it. Yeah, compared to, this should be faster because I am measuring. Yeah, in fact, look. Extremely fast, it seems to be, no? No, probably, yeah. Yeah, nevertheless, no? We can see very well here. I can zoom also, you can zoom also all variable if you want. No? In this sense, it's not so heavy the error in P0. It's not so heavy the error in P0 in the current. The reason is that we measure the current. This means we have information directly, intuitively explained. Intuitively explained. This means, yeah, the information is directly in, basically it's the innovation, represent the innovation through the current. But nevertheless, to obtain a good match, nevertheless, we need time. It could be that here P0 was the smallest. Let me check. So we can justify also this. It could be in accordance with what I see in in the simulations, it seems to be the smallest. Now here's the initial values. Oh. Seems to be, I don't know if it's the smallest. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. More or less the same order. It's difficult to explain why, because they are connected. How we can improve? Let me, for instance, to improve. In order to improve, to justify these words, I have to plot the element of the covariance matrix, because we minimize this. I don't have time to do. You can do at home. To look when we have lower and lower covariance matrix, because the algorithm minimizes the covariance matrix. If you look nevertheless without where is the current? Current is here. Yeah. But look in this. If you want, for instance, let me say, improving the error in the first part here, my idea, what we can do, where this error come from. I would like to say, I would like to increase Q corresponding to the current in order to trust more the measurements and less the model, because we can see that also observing here that we have the discretization in accordance, I think was Sarah asked me, no? This means increasing Q, in my opinion, will improve. We have to be careful, because to be precise, you have to look at the covariance matrix. But let me see this. I don't like this transient. And the transient could be improved. Look here, no? Because of discretization, probably the TS. Let me increase Q corresponding to the current. Let me show you this, and then we will do another exercise. No? This means let me increase this. If I increase in this without saturating, this is a little bit the problem which I told you also before last time. I am trusting more the measurements, less the model, because we have seen, because of this TS, probably TS is too large. We have seen a little bit this effect of TS. Let me show you now what happens. This is the result at this moment which I am waiting. If my reasoning is correct, something better, let me say better approximated in the transit. I don't know. Let me stop. So it should be enough. No, I don't know if we improved. But it seems, because before we obtain good result, 6 seconds. I don't know what was here. Should I come back in the example before? But it seems to be, here we can memorize 0,005. Let me see. More or less. No? Of course, we have more or less the same effect. But anyway, if you let me come back to the example as before. 0,005. Let me come back. This was 100. Yeah? Let me see what happens. Here is, let me consider here just to 5, 10 up to -3, right? I see. 5, 10 up to -3. What happens if I trust more the model? Changes? Not much. More or less the same, right? This means we are in a saturation situation, probably. Yeah, it seems to be, yes, 10 up to, again, -3. I don't know. To look at this, you have to build, I told you last time, an error integral of the error square. It seems to be that it didn't change much. Let me reduce again. Without sharing, let me reduce again. Let me see what happens. Yeah, now it seems to be that changed something. This is the value, no? 5. 10 up to -3. Yeah, it seems to be something worse. But of course, we have to, let me do the last test. We have to measure with an error. I do very small. Now should be more visible that the transient is not so precise. Let me see. We need more time. Yeah. Okay, now it's clear a little bit. We can see. Oh, clear, not really. Where is 0, comma is here? It seems to be in a not really big difference. It seems to be that we are in a saturating situation. Let me see R. R is this one. Okay. Look what happens. Now I clarify what happens. This is R, no? Or yeah, 12. Yeah, you can see that R is very bad represented. The reason is that we trusted the first equation. I put a very small value of the first equation. This means, in any case, the representation is not valid, absolute anymore. The reason is, let me come back theoretically. I cannot trust the first equation because r of t is a Gauss variable. This means the first equation in our representation is the most critical one together with the third one. This means the best way to represent is the relatively large uncertainty of the first equation because we have this variable here and the large value of r, or third equation. Let me show you this. But of course, the tune is a big problem because they are connected. No? This means, to conclude, yeah, how we can put these Q values. I told you we have a particular algorithm, which is not the goal of this topic, but I do sometimes in optimization problems by bachelor thesis. We can do with neural network, with particle swarm optimization methods. That now should be reasonable. Yeah, it could be that cannot be better than this one. Let me see R. R was, I don't know, this one? No. Where is R now? Let me see. Otherwise, I have to come back. R is here, no? Where is R? Second. R is here. To be more precise, everything depends on R. Everything depends on R. This means we can see as long as R is not correct. This means we have to invest energy in estimation of R to reduce the error in term of current and velocity. The reason is that R, the hypothesis of R, is the more conservative. We say that R is a Gaussian variable. As I told you last time, and of course, as long R is not estimated. Yeah, I am stopping. We don't have good results also for I and omega. Or better to say, the idea is to estimate as soon as possible R, because the uncertainties came from R. Okay, the idea is now to tell you something different, but I would like to conclude here. In January, I will go in depth on this with another example of this augmentation using an embedded file in MATLAB. And yeah. And then we will start with the physical nonlinearity. At this moment, the nonlinearity is an artificial nonlinearity because of the representation. And then the rest of the course, I try to show you some possible variations. I will tell you also one example in the outputs. No? I told you also today, H capitalized, H not capitalized. But before this, I don't know, before or after, I will show you some possible configurations and so on. In any case, this example here and the example which I will present in January very shortly are important because the augmentation, in order to estimate something in the Kalman filter, is extremely important because not all parameters are constant. How many parameters can I estimate? I will tell you before tell you about the variation of the Kalman filter. And this is related to the observability test in nonlinear context. Okay, I will stop now recording. If you have a question, we can remain here. I hope that